So, good morning to all. So, we will continue about the thermal analysis of brake system. So far, we have discussed various aspects. In fact, we have understood about the brake energy and braking power, and also in last lectures we have done about the how the brake power is absorbed individually with respect to lining aspect and also with respect to drum and disc aspect. In fact, the power absorption we have discussed in for all three types. When you talk about all three types, about single stop braking, repeated braking, as well as the continued braking. Okay. So now today's lecture we will understand what will be the temperature. I am talking about the temperature analysis during the single stop braking and also repeated braking, and finally we do with the continued braking also. So all three things we are going to learn from today's lectures. Just wanted to understand about the single stop braking. The purpose is I need to understand how much temperature, right, is going to be taken place between the rotor and the drum. That is the main motto, and I am sure you would know that in single stop braking the purpose is you are allowing the vehicle to maximum speed and apply the brake, right. That is what happened, and since the time is the braking time too small, there will not be any convective heat transfer, there will not be any heat dissipation from the things, only the heat transfer will take between the brake lining and the drum. That is what is happening, right, nothing else. So no convective heat transfer in single stop, and all braking energy is absorbed between the brake and lining. Okay. So in that case, how can we find out the temperature aspect? Okay. So the heat penetration, before understanding about the power, we need to understand the heat penetration. No convective heat transfer. Heat transfer in single stop braking. Okay, all energy, all brake energy, right, is absorbed by the brake and lining. Okay, by the brake, lining, and disc slash drum, or you can say rotor also, all are same. Disc, rotor are one aspect, the drum is other aspect, they are same. Okay. So heat penetration time to reach the outer drum radius, heat penetration time, you can say Tp, right, to reach the outer radius surface, outer drum surface or disc surface, is usually, it depends upon the length, it depends upon the length and what else, material properties, right, exactly, excellent. So it is depends upon the length and material property. So this L square by phi alpha, straight away take the equation where alpha is nothing but thermal diffusivity. So thermal diffusivity, this is nothing but alpha equal to K by rho C, right, K by rho C, K equal to thermal conductivity, okay, and rho is the density and C is specific heat capacity, right, capacity of rotor drum, either way is fine. Okay. So this is what happened. So the penetration, it depends upon the thing. So L, we know that L is what is the L? it's a thickness of the drum or disc half, it's half, it's not full. Okay. L is the half thickness of drum or rotor. Yeah, that's fine. Okay. So we need to understand, since we are talking about the symmetry aspect, so we want to know how the heat transfer taken from the outer surface to the mid surface. Remember, this is your what do you call it, disc or rotor, you can say that. This is your pad, right? This is your pad, both sides are there. So when these two rub, heat generated happens, right? The heat generation reach to the until mid of the rotor or drum. That's why we have to find out. So for disc, the drum, right, the time until the heat flux has reached the heat flux. So since we are talking about the thermal aspect, this is Q is the heat flux, but already you know that the heat flux nothing but your brake power, right? That's a brake power has reached to the the midpoint in solid disc or drum. Okay. Then that is T max, the maximum temperature you need to understand for given length Ti equal to 5/18 of then heat transfer, then the Tb, okay, I will tell you what is the Tb, divided by rho Ck square root of, and where Tb equal to your break time, right? It's your break time. Normally, since we are talking about for symmetry, right, for symmetry, the penetration time, right, usually the penetration time Tp equal to the break time, half of the break time, obviously. So when do you export the heat, how the heat is transferred? Until the vehicle stop, right? Until the moment you apply the brake, that's where the energy converted. Your kinetic energy is converted into brake energy. So from the moment you apply the brake till reach to zero velocity, right? So that's a thing. So that is your braking time. With the braking time, half of that would be the the penetration time to the heat penetrate at the midpoint of the disc or drum aspect. Okay. So this is the equation for a single stop braking aspect. Now we will move for the repeated braking, okay, for the repeated braking aspect. So what is the understand repeated braking, right? So yeah, before going to repeated braking, I would like to emphasize, since we are talking about the properties of the drum or disc, right? We talk about drum or disc, we are talking about properties, we are talking about density, specific heat, thermal conductivity K, and the diffusivity alpha. So this is the rho, okay, and C, K, and alpha, all the values for the respective brake lining, respect to pad, right, and the respective drum and disc is given. In fact, these are the value I have taken from brake design by Rudolf Limpert, okay, that is a book where I have taken this reference. These are the value, these are standard recommended value, these are the value we are going to use them for our calculations, okay. So these are the standard thing. Of course, there are slight variation if you use different material, but generally this can be taken for our analysis, yeah, This is the brake descent values. Now we will move on to the temperature analysis of repeated braking. So in repeated braking, similar to single stop, okay, similar to single stop. In single stop, you are allowing accelerating the vehicle to the maximum speed and apply a brake, right? Apply a brake to bring down to the 0 velocity, a complete stop. Whereas this is not the case, okay. This is what you do, you accelerate for a certain speed, then apply a brake to bring down to certain speed, or you can be 0 also. Again accelerate to the max one particular speed, bring down to the lowest speed, like that you keep repeating. So by doing that, you are allowing the system to cooling also, right? You are allowing the system cooling, whereas in single stop there is no possible for cooling. So since the cooling is taken place, obviously you would expect conduction, convection. Apart from conduction, you will have a convection also, right? That is what I have discussed in the previous lectures for repeated braking. Remember H, right? The convection of the rotor, then convection of the pad, those things we have discussed. In fact, we found out the heat transfer individually for the pad and the lining also, okay. So as I said, a vehicle is decelerated at a given deceleration from test speed to lower or 0 speed, after which the vehicle again accelerated to the test speed and the braking cycle is carried out repeatedly. This is called repeated braking. So in an analysis, what we are going to do, we will assume certain things. Disc drum is a lumped system, heat transfer coefficient and thermal properties are constant, otherwise it will be too complex, and the temperature is uniform throughout the disc and drum, and it is function of time, okay. What do you understand lumped mass? What do you mean by lumped mass? Yes, how do you understand lumped mass? You take some kind of sand, okay, if you hold it, it will form as a solid. The moment you crush, it should become crumble, right? That is called a lumped mass, okay. You don't take it as a, otherwise the analysis is difficult to achieve. So assuming this as a lumped mass and sorting out, okay. So by doing that, so you first apply a acceleration to the particular speed, break down, right. So there is a deceleration, again accelerated, decelerated. So this is happening with the cooling. So whenever you do for one cycle to second cycle to third cycle, there is always delta T will be increasing. Certain temperature rise will increase, right. So we need to understand what would be the temperature rise, right, of the rotor or drum, yeah, okay. So in fact, as I said, remember, so this is a repeated braking. So heat transfer is taking place. You can see that this is the where the rubbing is happening, right. So you have a convection of your disc, convection of the disc. You can see that, and there is a conduction takes in place. Again, this is the where again conduction happening. One conduction. There is one more conduction between your the brake lining as well as the pad also, right. That is also there. I think those are things we have discussed in the previous lecture. In fact, I would have drawn this similar to this diagram, remember, right? Yeah, this is what I would have drawn also in the last lectures. You can see that. So this is half of your rotor, right, and you can see this is the convective heat transfer aspect. Then this is the your conduction thing. Then again one more conduction happening between your the pad and the lining things, yeah. Just wanted to make sure that you understand that for repeated cycle, assuming that this is I am drawing with the time, with respect to time, this is a t, okay. You say that this is acceleration or deceleration, it does not matter, either way it is fine, okay. So initially what happened, you will make sure that you will reach certain height, right. Then you apply the deceleration to bring down to certain speed. Again increase, accelerate, decelerate, right, and accelerate, and this so on. This is what happening. Okay, this is what happening. So if you look at, this is the time, right. So the actual braking time happening when you reach the maximum speed to the deceleration thing. This is your braking time. This is your braking time TB. So what is this time? What do you call this time? Maybe I will say that. So this has been done. This has been done. Now I am increasing this my acceleration rate to speed. So what do you call this timing? What is this time? It's a cooling time. There is no brake, right? You are not applying. It's a cooling time. You are allowing the brake to cooling time. So this is your TC. So this is the total braking total time. This is the total one cycle time. So within that you have a braking time and cooling time. Both are there. And if interesting, you can look at, normally your cooling time is much greater than your braking time. Okay, normally cooling time is much greater than things. So okay. So we want to understand within the braking how much temperature is going to be rise in the brake system. Okay, the increase in temperature of rotor or drum, delta T I need to understand. So delta T is again the amount of heat absorbed in the rotor QR, right. Then your braking time, then what else you expect? Your thermal diffusivity, right, rho Ck, rho R, Cr and Kr. So this is the delta incremental temperature increasing. I am sure you know Qr equal to brake power absorbed by the rotor, and you know that, right, these things are understood. So the rho is density, C is a specific heat capacity, right, then K is thermal conductivity, and suffix R indicate about the rotor, right, suffix R indicate about the rotor thing. Okay. So as I said, we are now I know what is the temperature for one single cycle when you apply a brake, right, from acceleration to these things. Now I need to understand about the lumped formulation results in a differential equation for what is that, cooling off the brake after the nth brake application. So I am straight away going for the equation rather than the giving you. Okay. So I need to have a two equation. What is that temperature before applying a brake? That's one equation. And what is the temperature after applying a brake? That's what I need to understand, right? So for the nth brake, assuming that for nth brake, temperature before again nth brake application, right, this is T of T, this is B suffix for before applying a brake. Okay, before applying a brake, 1 minus e power minus of Na minus 1, okay, into HR AR TC this is over, okay, then divided by rho r C r V r, okay, this is fine, yeah, into e power minus h r a r t c divided by rho r C r V r, okay. So yeah, this is again bracket, close it. So with the delta t, so this much information is there and divided by 1 power e power h r a r t c divided by rho r C r and V r, okay. So now I will say that what is that NA? NA is nothing but number of break application right, and HR is the heat transfer coefficient, okay. What do you mean by A? R surface area of the rotor, surface area of the rotor, any other term VR means swept volume of the rotor, okay. Any other term are we missing here? We know HR, we know AR, TC is the cooling time, rho C all are known to you, just a new term we have volume, yes, I think volume we have, and H is already have discussed things. So this is equation, you can say that number 1. This is before nth break. Now we need to understand the relative temperature after the just one more information. T infinite is your ambient temperature or room temperature, okay. This is the ambient or room temperature. Shall I move on to? Yeah. So the relative temperature after nth break application, so T of T, T infinite, this is A. So B is the before application, A is the after application, is 1 minus e power n minus 1A, right. Now because of that is before one cycle, now that one cycle is over, so you will have only NA, HR, AR, TC divided by rho R, CR, VR, okay. So the whole thing into increasing delta temperature T, then 1 minus e power minus HR, AR, TC divided by rho R, CR, VR, okay. So this is the, you can have equation number 2, this is 2. So you have to find out relative temperature of before nth application and relative temperature of after nth application. So this is the way you need to find the relative temperature in repeated braking system, okay. Now the last one I'll move for the temperature analysis for continued or drag application. Yeah, this is a simple equation. Continuous braking, when the brakes are applied during the downhill, right, during the learning. So, cooling must be always considered, right. Yeah. So, what do you understand? Okay. So, I am sure you know single stop braking, repeated braking is fine. In continuity braking, what is the purpose of continuity braking? You are in the downhill, right, the vehicle is downhill, you need to move down, right, you need to move down. So, the purpose of braking, what is that? You want to stop the vehicle or you want to control the vehicle? You have to control the vehicle. That means you have to maintain the certain speed such a way that the vehicle is keep moving, right, such a way that you have to apply the brake, understand, right. So, here the purpose is not about the stopping, but controlling, so that should not have any catastrophic failure, that is the way. So, when you do that, so will you apply deceleration suddenly very high? No, right. You know, you will apply a small amount of brake and allow the continue things. That means it is kind of repeated braking, but okay, but not exactly, but completely different from the single stop. Okay. So, obviously there will be a cooling system also, right, there will be a cooling system. So, in the case the temperature response, see, if you want to understand the complete how to get this temperature aspect with the heat transfer, I can refer certain books, you can go and study, right. Drum and disc, right, during, it is called the drag braking. What do you understand drag? What do you mean by the another literal meaning of dragging? What do you understand? Yeah, drag means keep, stretch, right, you keep allowing the system, but in controlled manner, that is called dragging, right. So, in a drag, so when you do that, usually you will have one initial temperature, right, you will have one initial temperature apart from the ambient temperature. As you are applying, so the heat is generated, but again certain amount is dissipated during the cooling time also. So, we need to understand what is the exact temperature you would experience during the drag aspect. Okay, T of T, small t, Ti, T infinite, Qr is the heat absorption, okay, by HR AR. Remember, you have a cooling also, so there is a convective heat transfer, okay, into E minus HA, sorry, should be HR AR T rho R CR VR. So, this one thing, then again you will need to have your ambient temperature plus QR, HR and AR, okay, this is a thing. So, where TA is the initial temperature, T infinite is the ambient temperature, okay, and T of T is the final temperature. T of T is always final temperature irrespective of the repeated braking or continued braking, okay. I think these are the thing you need to understand for the thermal analysis. Of course, still one more topic we have to see, where is the design limit, what is the design, whether what are the material you have chosen, right, whatever the vehicle weight, the power and the size is sufficient for the given the brake, that those things we are going to discuss in later class. Let us do some couple of small problems, okay, so that understand about this braking aspect, okay. Problem number 9, we did the problem number 8 for the selection of the brake lining, remember, based on the SAE code, okay. Now, we have problem, Federal Motor Vehicle Safety Standard 105 required burnishing of the vehicle of the brake at gross vehicle weight GVW from a speed of 64 kilometer at a deceleration of 3.66 meter per second square for 200 stops. Okay, this is for 200 stops. The cycle distance is 1.61 kilometer and the approximate cooling time is clearly given 88 seconds. Okay. Compute the average brake temperature after 5th, 10th, 200th stop. Use the data that follow. So, the vehicle is moving on a plain road with the deceleration rate is clearly given. So, you need to identify the temperature for a 5th, 10th and 200th stop. Okay. Use the following information. 15% of total brake power is absorbed by the one rear brake. Okay. The brake drum volume is clearly given. What is the volume? The brake cooling area AR is given 0.051 meter per square. Then convective heat transfer coefficient also given, and the vehicle weight is given. So, is this what is the problem? Is this repeated braking or drag braking? It is a repeated braking. No, it is repeated braking. Okay. So, the data clearly given. You have the vehicle weight is 16.458 kilonewton. That is clearly given. So, then the deceleration rate also clearly given, and the distance also given 1.61 kilometer, and the cycling total the approximate cooling cycle time is given 88 cycle, that is also given. Then H also given. Okay, H is given, AR given, VR, AR, all those given. What are the other information missing? Your density rho r, right, and your specific heat capacity CR and thermal conductivity KR, those values are missing. So, those values you should take it from this table. So, you choose your density value 7 point, please write down the values, please write down the values, these are the value you need to know. So, you need to have a density, C specific heat capacity, and K thermal conductivity and thermal diffusivity. Okay, depends on the equation, we are going to use all those values. So, how are you going to solve this problem? First of all, we have to understand how much heat is absorbed by the rotor, right? That is the first step. How much heat is absorbed by the by the rotor, that is the first step we need to understand. Okay. The P average or else, okay, QR, the heat absorbed by thing, right, the of the rotor QR. So, you need to know the Km, remember the equation Km W V1 A, yeah, V1 A by 2G, this is the equation we have earlier, right. Your W, how much W? 16.48, right, yeah, 16.48 458, those that much kilonewton, that is clearly given. Km is not given, so we assume that Km equal to 1. Okay, what is the velocity? What is the velocity? 64 kilometer. Okay, 64 into 10 power 3 by 3600, right? Yeah, per meter per second. That's the velocity will coming. So, your deceleration rate is 3.66, 3.66, so much meter per second square. Okay. So, 116,458. Can you tell me what is the V1 value? 17.78 meter per second. 17.78 meter per second. With deceleration rate 3.6 divided by 2 into 9.81. This much energy is developed. This much energy is developed. How much energy is absorbed by the rotor? 15%. That is what is given. So, 15% means into 0.15, right. because that is the energy only we want, right, not the entire brake energy, that too the rear aspect. Okay. So, can you tell me how much energy you are getting QR? I think you must be getting 8.188 so much kilowatt. This much energy should be absorbed by the your rotor. Okay. Yeah, that's one thing is there. So, what is the braking time TB? What is the braking time TB? V1 by A, right? V1 by A. So, 17.78 divided by 3.66, that should give me 4.9 second, right. But the total cycle time, so even though it's a cooling time is given, the total cycle time including cooling time, how much is it? 88 seconds. 88 second is given. Remember, when we discuss about delta T, we always ignore, because your cooling time is much higher than your braking time. Now you can see that how much 4.9 second is your braking time out of 88 seconds. So we have enormous time for the cooling aspect. Okay. So now that's done. Now the second aspect, we need to find out what would be the delta incremental. That is constant all the time, right? Delta T is always constant. I had to find temperature rise. So what is the delta T? We got already, remember? Delta T equal to your QR TS, right? Rho R, CR and VR. 8.188 into 10 power 3, right, and 10 power 3, what is it, your timing? 4.9, right? Yeah, 4.9 TB. Can you substitute the rho R, CR, VR value and tell me what is that value you are getting? Maybe I can rewrite, rho R should be 7228 so much kilogram meter cube. CR, what is CR? 419 joule per kilogram Kelvin, and VR already given, VR equal to 0.0057, right? Yes, 00057. Okay, 00057. Okay. Yeah. Can you tell me what is the value you are getting? I think you should get 23 Kelvin, the delta T. This is the value you should expect, right? Delta T is 23 Kelvin. So initially we found out what is the brake absorbed by the rotor. That's one step we have done. The second step, we are able to find out the delta T for each cycle is going to be. Now we have to find out the temperature rise after 5th, 10th and 200 cycles. That's what we are going to do that. So that means we have to choose equation T of T things. This is the after, right? This is the equation, we should use it. HR, AR, TC, okay. Rho R, CR, VR into delta T, yeah. HR, AR, TC, divided by rho r CR VR. Okay. So this is the equation you have to utilize, okay, for calculation. Yeah, this is the equation you have to utilize. And in fact, so the NA we have to use it 5, first problem for 5 cycles, then NA equal to 10, then NA equal to 200, right. For each 5th cycle, 10th cycle and 200 cycle, we need to find out what will be the final temperature, okay. So we can assume your infinite the ambient temperature equal to 299 Kelvin. Let's take this is the value, right. You assume it your temperature, the ambient temperature. Yeah. So what I am going to do, I will straight away come with the answers rather than substituting. I will show the method how to do it. You do it at home. So I am going to straight away give the answer for 5th cycle, right. For 5th cycle, my T infinity T, I will say this is the T5, T infinite will be 72.97 Kelvin, and I am sure I know your ambient temperature is 299 Kelvin. Yeah. So the T5 would be 378 Kelvin, 378 Kelvin T5. Similarly, okay, if you do for T10, right, for nth cycle 392 Kelvin, for Na equal to 10th cycle, Na equal to 200 cycle, T 200, okay, if we do that 399 K I am getting. So what is your observation? So at the 5th cycle the temperature 378, at 10th cycle temperature is 392 Kelvin, and 200 cycle the temperature is 399 Kelvin. So what is your observation? Remember the gap between a 10th cycle and 200 cycles. The 10th cycle the temperature is shown 392 Kelvin, whereas 200 cycles shown 399 Kelvin. So what is that gap? Only 7 Kelvin is the difference. In other words, the maximum temperature observed by the break, right? The maximum temperatures is it's not observed, it's achieved within the few cycles. Am I right? For T5 already I have reached 378, okay, 10th cycle 392 Kelvin, only shy of 7 Kelvin, right, for 200 cycles. So even though you do, how do I say that, you do repeatedly, right, the maximum already achieved within the few cycles, then you will ask question, then why it is not increasing? Obviously you are allowing the cooling time. So this is, understand now, the cooling time it takes place to maintain that whatever the maximum temperatures attained in the break, okay, right. You may ask question, why we are doing, you are talking about single stop braking, then you are talking about the repeated braking, then talking about drag braking, drag stop braking. Why we are doing in 3 different aspects? What is the reason? Just think about that. Those aspects I will discuss in next class. Okay. Yeah. Thank you.